All right. Hope everybody's having a good day. Just a couple of items. We're turning in the inverse homework today. We will talk about it in just a moment. Even if you don't have it ready right now, get it to me by the end of the day. You'll still get your points on the point bank. We have a quiz over that on Friday. Let's see, we're still a ways out, but Monday the 14th is going to be your first exam. I'll let you know what's up on that as soon as we get a little closer, probably near the end of next week. Did I mention the waivers yesterday? I don't remember if I did or not, but if you're in a situation where you're in an upper level class and you happen to have failed the first 6 weeks, if you need a waiver for some kind of extracurricular activity, you can get those from Mrs. Edwards, Mr. Young's secretary in the office, and I believe they're due to him no later than Friday at noon. So if you're in that situation, it's one of those the sooner the better type things. Okay. Did I mention the digital textbook? Okay, so if anybody's interested in that, I've already had a few people come talk to me. You can't immediately go to the website. You have to let me go ahead and assign the material to you in the website. It's set up very strangely. But once I assign the material to you, then you can go in and go ahead and use capital LBB 1000 number for your username and password. And it'll go ahead and allow you to download that. It's just if you're looking for an extra resource, because several people are typically asking me for extra practice problems or things of that nature to prepare for quizzes and tests. And it covers all the material we're going to have this year. It's got extra problems. I believe it even has video tutorials. So it's a really good resource if anybody's interested. I just have to assign it to you beforehand. It won't let me do it by class. So. Okay, the only other thing, I have some rather exciting news, or hopefully it's exciting. Tomorrow we have a young man from Texas Tech who's going to be joining us. He's a teacher candidate. So think about a student teacher, but he's only going to be here on Thursdays. Okay, and it's only going to be through Thanksgiving. So it should be the last Thursday right before Thanksgiving. So he'll be with us for a couple of months. I'm not remembering his name right off the top of my head, but he'll have the opportunity tomorrow to go ahead, because I was just informed about this yesterday. So he'll have the opportunity to talk to you guys tomorrow, kind of introduce himself. And I think in the beginning, he'll probably go ahead, maybe do like a focus activity or something, and then probably build up to a portion of a lesson that we have on Thursday. Okay, we'll kind of see what happens. Okay. But any questions? Okay, well, let's get started with the inverses. Are there any questions on the assignment? Inverses of functions. Hey, a couple of these right here? Sure, okay. Now, what I thought was the best way to do it, I mean, you've got some piecewise functions here made of linear functions. I just went ahead and graphed the inverse, and then I just did this all visually. So, for example, we have this point right here, which is negative 4, 4. So I know that point's going to be 4, negative 4. And then I kind of just went down the line. We had a 0, 2, 2, 0. Okay. And then we have a 2, negative 2. So that would be negative 2, 2. Okay. And then we finish up with 4, negative 3. So negative 3, 4. Okay. So there's F inverse. And then I'm going to do the same thing for G. Unfortunately, this one's going to go a little off the grid, and that's okay. So negative 4, negative 3 would be negative 3, negative 4. Negative 2, 1 would be 1, negative 2. Okay. And then I think I made that a little too high. Then we have 1, 4, so that would be 4, 1. And then this last one here is the one I was talking about, 3, 7. So 4, 5, let's say 6, 7, and then up 3. So maybe something like that. So like I said, a little off the grid, but that's okay because that portion actually isn't used, thankfully. Okay, so like the first one, what am I wanting to plug 0 into? F inverse. Okay, so I want to look at this first one that I sketched. So when x is 0, I have the 0 right here. I'm just going to go straight up. Looks to me like F inverse of 0 is just 1. Okay, would you guys agree? Okay. Now, Fernando, were there certain ones you wanted me to look at, or you just want me to choose a couple of random ones? 18? Okay. Now, what does this open circle mean? Okay, that's composition. Remember, this is the same as saying F inverse of G inverse of -1. Let me give myself a little more room here. Okay, so the first thing I want to evaluate is G inverse of -1. Okay, so I'm going to look over here. This one's the one I graphed. G inverse of -1, I would probably go ahead and say -3. Would everybody agree with that? Okay. So then I'm looking for F inverse of -3. So now that output for the inside function becomes the input for the outside. So I'm going to plug -3 in here, and it looks like I'm going to get +4. Okay. Fernando, is that what you got? Okay. All right. Yes, ma'am. Actually, yeah, you can do that as well. Someone brought that up in second period. That's actually a really good idea. All done? If you'll put that in the tray, ma'am. Okay. Anything else? Number 6. Yeah, we're not in the middle of the lesson, so grab the password quick. Number 6. Okay. Is it not number 6? Was it one of these? One of the first ones? No.
I think it was number 5, actually.
Number 5? Okay. Number 5? Okay. So let's see here. F of x equals 1/2 x plus 3 squared minus 4. So it's a quadratic. It says use a graphing utility to graph each function and use the horizontal line test to determine whether the function is 1-to-1 and has an inverse. So really on these, it's just either a yes or a no. Now it's either going to be an inverse relation or it's going to be an inverse function. Like this one here, we know the -4 is going to shift him down. What about that +3? Shift him left, remember we take the opposite, and then we want half vertically. So how's that going to affect the quadratic? Is that going to make him fatter or is it going to make him skinnier? It's going to make him a little bit wider. Not by much, but it's going to make him wider because I want the y values to be half of what they originally were. So if I were to say -3, -4, okay, it's going to be just a little bit wider. We're not talking huge. I'm just going to draw something like that. And it really doesn't matter, how wide this guy is. Would the inverse be a function? Okay, no, because I go ahead. No, on these you did not have to find the inverse. In fact, on this one, that one's super fun if you try to find the inverse. But we're not going to worry about that right now. I'm not going to have that. But you look at the horizontal line test. Okay, because remember that's a visual way of telling you if any y values repeat. And why is that important to an inverse? What would those repeating y's become? Repeating x's. So this guy right here, you will be able to find an inverse relation, but will it be an inverse function? No. Okay. Oh yeah, you did that. All you had to do was just basically say yes or no by the horizontal. Okay. All right. Anything else? We feel pretty good. Hey. What? 22. Okay. So let's see here. The consumption of bottled water in the U.S. in gallons per person from 2005 to 2011 is shown in the table. The time in years is given by T, where T is equal to 0 corresponds to 2005. All right. So this is during that year. This is 1 year later, 2006, all the way to 2011. So this is the number of gallons per person. Wow, that's a lot. So what does the inverse represent? So let's first make sure we understand what the function is saying. Okay. If I input the year, what's my output? The number of gallons of bottled water that people are going to drink, right? So what would I be doing with the inverse? What would the input be? It'd be the number of gallons of bottled water, and that would output the particular year. There we go. I'm just going to go ahead and talk about it instead of writing it out. Okay, but does that make sense? Kind of think about what we did in the lesson when we were doing, I believe it was the height of a tree and the amount of water it needs. Okay. But now, this one here, would the inverse be a function? Yes or no? I already see some people shaking their heads no. What's wrong with it? We have some y values repeating. So if I did invert it, they'd be repeating x's. So it'd be an inverse relation, but not an inverse function. Okay. Fernanda, is that good? Okay. All right. Anything else? Okay. If you do end up having any other questions, please let me know. All right. First focus activity of the year. Or, well, I should say 6 weeks. And really, I should be saying grading period. Keep doing that. Okay, so this is number 1. I got the idea for this and the next focus activity from the composition lesson last week because there were several people who didn't remember how to solve an absolute value equation. And I got to thinking, well, how many people would be able to solve an absolute value inequality? Does anybody remember the steps, or has anybody solved these problems here? Okay. Now, normally, way back in the day, bless you, I'd go ahead and teach this using an analysis method, because you'd want to go ahead and look at every case. If x were 0, if x were positive, or if x was negative. And you go ahead and test each. You take the intersection, combine your answer with a union. Unfortunately, you know, the amount of material that we have to cover in the time given, that's one of the lessons that kind of just had to go away. Maybe if we have time at the end of the year, I would love to go ahead and show that. I'm just going to teach you the shortcuts, which is more than likely what you were shown way back in algebra. Okay, so you'll notice that I've got this silly little statement here. More is or, less is nest. It's one of those little items that it's ridiculous to say, but it does tell you exactly what to do. What do you think the more means? Greater than. Okay. So what this means is if it's a greater than inequality, you're going to create 2 inequalities and you're going to take the union of the answers. Okay, so what I'm going to do, if I had this statement right here, I'm going to first say 3x minus 12 greater than or equal to 6. So the first one looks exactly as the original, just with no bars. Or I'm going to say 3x minus 12, and I'm going to change 2 things. Okay, the symbol reverses itself. So greater than or less, or greater than or equal to becomes less than or equal to negative 6. You change the sign of your constant. Okay. And then you just go ahead and solve these like a normal inequality. 3x would be greater than or equal to 18, so that x is greater than or equal to 6. Or 3x is less than or equal to 6. Okay. And x would be less than or equal to 2. There you go. So graphically, you're going to have 2 shaded regions of answers that would make this true. Excuse me. So if I were to go ahead and write this as a interval notation, which is what we usually like to do, negative infinity to 2, union 6 to infinity. Okay. All right. How many people had that answered before we started? Okay, good. Okay. Now, does it matter if we have equality or not? Like the first problem is greater than or equal to, but the second problem is just greater than. Does that change anything? No. I mean, now it'll change in the answer that you'll have parentheses, but as far as the process, no, it doesn't change a thing. So the first one would be b minus 4 is greater than 6, or what? B minus 4 is less than negative 6. You switch the symbol, and you go ahead and take the opposite. Now, you'll notice this focus activity had both greater than. So what do you think the next focus activity is going to have? They're going to both have less than. That's where we'll be looking at less is nest. Okay, and I'll explain what that means when we get there. Okay, so in this case, either b is greater than 10 or b is less than negative 2. All right, so what would be my interval notation, my answer? Negative infinity to negative 2, parentheses, because it's no equality, union 10 to infinity. There we go. And that's it. Does that seem familiar? Now that we got to talk about it, you remember the good old days of algebra? Okay. All right, good, 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 good. Now, why are these focus activities important? Because what? Well, it is practice. I mean, that's good for, ideally, but I'm thinking in terms of your average. I hate to say free 100. I like to say guaranteed. Okay, but even that's not totally true, because a lot of the reason why some people's averages in the first 6 weeks were lower is because some people never bothered to turn those in. Please make sure you're keeping up with these. Okay, that is a guaranteed grade. And it becomes even more important now. You remember I'm talking about the restrictions that I've had because of the number of copies I made? In fact, did you see what I did yesterday with that quiz? I shrunk it so it was half a page. I'm trying to think of things that are saving me paper. Oh, thank you. Okay, Fernanda. So I am really only making like 2 extra copies of these assignments, these focus activities, and everything. So I know in the first 6 weeks, we had additional copies where if you lost or misplaced one, but that's going to become even more crucial this 6 weeks because I just won't have near as many copies. Okay, so please put those someplace safe. Don't lose them. Okay. Remind me how far we got. We talked about radians, right? Okay. Did we do this? Did we do the common radian measures? We did. Okay. Did we start to convert? Okay. So we'll go ahead and start there. But let me go ahead and give you a few extra examples. I got some on my paper. Now we're talking about radians. In just a minute, we're going to go ahead and compare them to degrees. And I'm going to show you a really simple conversion expression to go back and forth between the two. But what is 1 revolution in terms of radians? Okay, it's 2 pi. Okay. So I'm going to say 0 radians. We go all the way around to 2 pi radians. So let's fill in the rest of this, because we're going to be accustomed to seeing a circle with our coordinate system right in the middle. Okay, so half of that would be pi, half of the half, or 1/4 of the revolution would be pi over 2. What's 3/4 of the revolution? 3 pi over 2. Okay. Now, all these are positive, so I would have to be rotating what? Counterclockwise. Okay. But if I were to rotate clockwise, that would give me a negative. So I'd start with 0. So you're going to see the same values. They're just going to be going clockwise. So negative pi over 2, then negative pi, negative 3 pi over 2, negative 2 pi. Okay. So let me give you a couple of these. Practice real fast. Did I give you any yesterday? Did we even try those? Oh. Okay. Did I give you, all these classes are kind of running together. Did I give you 7 pi over 4? Okay, try that one, and I'm pretty sure I did not give you this one. Negative 17 pi over 6. Okay, I want you to try to sketch those for me. Find me the quadrant that these radian measures would fall into. Okay, let me give you about a minute to take a look at that. And then I'll kind of walk you through, show you how I like to do it. So 7 pi over 4 and negative 17 pi over 6. All right, while you guys are doing that, I'm going to go ahead and erase that. Okay, there we go. Dadgummit. There we go. There we go. All right. Do, 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 do. Okay. And the one thing I always do when I'm trying to figure out where these terminal sides are going to be, I always look at the coefficient. So in this case, 7 pi over 4, I mean, we're looking at 7/4, right? Now this is different from the ones we've looked at previously because these are improper fractions. One thing that's really helped me out, if it's an improper fraction, I write it as a mixed number. Okay, so can anybody tell me what quadrant would 7 pi over 4 fall in? Okay, so Natalia says the 4th, Connor says the 2nd. Okay. Noe, what do you think? First? Okay. Ooh, do I hear 3? Go. Hello. Oh, okay. All right. Well, let's see. Okay. So far I've heard 1. What'd you say, Connor? 1, 2, and 4. I will say one of those folks is correct. Okay. All right. One of those folks is correct. Jake, what do you think? You think what? It's 4 as well? Okay. We'll say it is 4. Okay. Now let's talk about that. What would 7/4 be as a mixed number? 1 and 3/4, right? So this is the same as saying 1 and 3/4 pi. Okay. So the whole number, okay, I'm going to start at standard position. Remember, that is the positive x-axis. So all I want to do is go 1 pi. So there's 1 pi. That takes care of him. But now I want to go 3/4 pi. But remember, in a revolution, pi is only half a revolution. So I want to go 3/4 of that half. So that would be 7/4 pi. In fact, the first one we did yesterday, the negative pi over 4, those are angles that have different measures but the same terminal side. What are those? Starts with a C. Coterminal. There we go. They're coterminal angles. All right. Well, let's try negative 17 pi over 6. Okay. Anybody want to tell me? Anybody think they know by show of hands what quadrant this is in? Philip, what do you think? Not second. You're close. Oh, it's the third. It's the third. Okay. Michael, is that what you were saying? Okay, let's see. What's negative 17/6 as a mixed number? 3. Ooh. 2. Okay. So it'd be negative 2 and 5/6. Okay. So that's pi. Okay. So the only thing here is that it's negative. I'm going to be rotating clockwise. So remember, I want to start with the whole number. So this is negative 1 pi. There's negative 2 pi. So that takes care of the negative 2. But now I only want to go an additional 5/6. Okay. So again, think about the coefficients that you have. How would 5/6 fall when it comes to like 0, negative 1/2, and negative 1? Okay. Is negative 5/6 greater than or smaller than negative 1/2? It's smaller than. Okay. Remember, the further you rotate clockwise, the smaller it becomes. So it's probably going to look something like this. You only want to go 5/6 the rotation of pi. And don't worry, I mean, if you're still a little hesitant on this, we are going to be practicing this a lot. Okay. You're going to be able to do this very, very quickly by the time we finish. It's going to take some time, but we're going to get there. How's everybody doing? Okay. All right. Okay. Well, we've been talking about radians. We've been talking about degrees. So now we want to know, how do I convert from one to the other? In a very, very, very simple process. If I have a degree measure and I want radians, I'm simply going to multiply it by pi over 180. Now I'll go ahead and put the degrees here. Okay. Pi over 180 degrees. Oh, wait. Oh, yeah, that's right. Second guess myself for a second. So if I multiply a degree measure by pi over 180 to get radians, what am I going to do if I want degrees from radians? 180 over pi. I'm going to multiply by the reciprocal. There we go. Okay, so let's do a couple of these together, and then we'll go ahead and try some on our own. So let's see here. Hello. Okay. Emma? All right, so I've got 7 pi over 6. Now, you want to be careful. It's pretty obvious that this one's in radians because of the what? Pi. But you can have a radian measure that doesn't have pi. That's very, very easy to do. So you're going to notice, you'll know absolutely for sure if it's degrees if it has that symbol. Okay, if it has that degree symbol. So you want to be really careful about that. So I've got radians, but I want degrees. So according to this, I'm going to multiply by 180 over pi. And notice, what's the first thing that happens? Those pi's cancel. All I'm left with are the degrees. Okay. Now, you can multiply 7 times 180 and then go ahead and divide by 6. I prefer to simplify before I do that. What's the common factor between 6 and 180? It is 6. 6 goes into itself once, but how many times into 180? 30. So 30 times 7, this is equivalent to 210 degrees. Okay, just a very, very simple calculation to go from one to the other. Now, let's go from degrees to radians. So I'm going to multiply 135 times pi over 180 degrees. And you'll notice it's the degrees that cancel this time. All right. So 135 over 180, let me go ahead and write this out. Does anybody know the largest common factor? 15 is good, but it's not the largest. But we can go ahead and just simplify it. We can just break it down if you want to. Okay? Oh, very good. Presumption, what'd you say? You are going to get 3/4 pi. The largest common factor actually turns out to be 45. Okay, 45 will go into 135 3 times, 180 4 times. But typically, I'll just go ahead and start here. What a lot of people have been telling me today is 5, because that's pretty obvious that it's divisible by 5. So the first thing people have been saying, okay, that's 27 over 36. And then I can, a lot of people started, they noticed 9 here. So that's where I got the 3/4. But think about it. I used a common factor of 5, then a common factor of 9. So that's where I'm getting my common factor of 45. Okay. Easy? All right. Try those next 4 on your own. Okay. Let me give you about a minute. You got 2 radians, 2 degrees. Okay. So write out what you think the equivalent radian and degree measure will be. And then I believe we just have a few questions left on the packet, and then we're done with the notes. Okay, so it may not be done, and that's okay. We're just going to go row by row because of the blind that I have up here. So anybody tell me what they get for B? What degree measure is equivalent to negative 2/3 pi? Negative 120? And what about E, negative 320 degrees? There we go. Perfect. Negative 120 degrees and negative 16/9 pi. Okay, how many people got those right? Okay, good, good, good. The conversion, like I said, is very simple. What about C, negative 8/15 pi? Negative 96. And what about F? Okay, so that one was a little lower, but I did hear some people say negative 11 over 18. There we go. Negative 11/18 pi. All right. Does anybody want me to talk about any of those? Okay, degrees to radians, radians to degrees. Anybody having trouble? Okay, good, good, good. Well, let's take a look at this last section here. Okay. We still got a decent amount of time. So let's just start with number 1 and let's see how far we get. How many radians is each angle of an equilateral triangle? Okay, well, let's go ahead. Again, I'm a very visual person, so I'm going to go ahead and start by drawing a triangle. But what makes it equilateral? Okay, the fact that all sides are congruent, that's equilateral. Now, for triangle, this is kind of unique, but if it's equilateral, that means it's also equiangular. There we go. Now, this isn't part of the problem. I'm just kind of curious what you remember from geometry. If a figure is both equilateral and equiangular, what do we call that type of figure? Starts with an R. What's that, Philip? No, not right.
Wait, it's like regular.
Regular, that is correct. Very good. We call that a regular figure. All right. Well, if it's equiangular, well, we know all the angles are 60, right? So really, I'm just converting 60 degrees to radians. What do I multiply that by again? Pi over 180 degrees. The degrees cancel out. Well, what's a common factor this time between 60 and 180? 60 itself. Okay, so you should be ending up with pi over 3 radians. Okay. All right. Now, these problems here dealing with a clock, there's different ways to look at it, but the first thing I'm going to go ahead and say is I know that a clock rotates clockwise. You know, that's how we get the term. It rotates around the right. But here we're just talking about the distance. It's just practicing converting these. So we're not worried about making the angles negative. Okay. We're just converting. Is everybody okay with that? Okay. So the fact that it's rotating clockwise, I'm not worried about the negative. So the minute hand of a clock travels how many radians in 15 minutes? Okay. So there's a lot of ways you could look at this. If we're looking at this as a conversion problem, let's say we have 1 full revolution in degrees, which is 360. Well, would everybody agree that 15 minutes is 1/4 of that, right? So 90 degrees. So would everybody agree in 15 minutes the minute hand moves 90 degrees? Well, that's all we're trying to convert. Okay, which, absolutely right. Natalia says pi over 2. Kate. There you go. Okay. So times pi over 180 degrees. So that is correct. That is pi over 2. Okay. There you go. Or if you know you're just thinking about you're wanting your answer in radians to begin with, maybe you don't need to convert it. What's 1 full revolution in radians? 2 pi, and you just want to take 1/4 of that. Okay, the same kind of logic that we were talking about. All right. Well, let's take a look at number 3. The minute hand of a clock travels how many radians in 10 minutes? So anybody have an idea for this one? It's more than 45? Okay, that's true. Well, think about it. We were just looking 15 minutes represented 90 degrees, right? And if we're looking on a clock, these numbers are spaced equally apart, right? So it's divided into 3 congruent sections. So if 1/4 is 90, then basically what's 2/3 of that?
60.
That would be 60. That's the 10 minutes. But didn't we actually see that a moment ago? What was 60 degrees times pi over 180 degrees? We got pi over 3. And I mean, here for the next one, you could probably just kind of use, logic to help you out. If 15 minutes was 90 degrees, 10 minutes was 60 degrees, then how far does the minute hand rotate in 5 minutes? 30 degrees. Okay, so how many radians would it travel there? 30 degrees times pi over 180. What's this one? Pi over 6. Yes, 30 again is the common factor. There we go. What do we think about radians? They're rad.
Wow.
You know, I think I missed my calling. How many people would pay to come see me talk about math? Hey, I got some hands going up. Nice. Hey, maybe I should have. I'm going to go home tonight. Hey, honey, I'm quitting my job. I'm going to become a comedian. I'm sure that'll go over really well. Okay. Let's try these last two right here. What's the measure of theta in radians if x equals 45 degrees? Okay. Somebody want to come on up and help me with this one? I'm sorry? Okay. So we know this measure right here is 45 degrees. Okay, so I really don't want to say anything because that pretty much gives it all away. Who wants to help me out here? The sooner we do it, the sooner we're done. Even that doesn't help? Noe? I thought you just raised your hand. Are you sure? Connor? Okay, Connor. Yes, ma'am. From the 52. Show me what you're talking about.
I got confused. I was thinking of like the pot or the radius.
The for 1 radian. Not in this case. Because see, we know that one section is 45 degrees.
Oh.
Okay. So this is exactly right. Where did he get the 315 from? Yeah, he just subtracted from 1 full revolution. So now he knows that theta has got to be 315 degrees, but if we want it in radians, there we go. It is 7 pi over 4. And in fact, does that one look familiar? That's one of the examples I gave you just a little while ago. Okay, good. All right, excellent. Who wants to help me with number 6? And then we're done.
Yes, I'll do it.
Will, okay. All right.
So, a straight line, which is just pi. So you can say that 6x equals pi. X equals pi over 6. Theta equals 5 pi over 6.
That's perfect. That's exactly right. In fact, I really like the way he did that. Everybody in the other classes today so far has been setting it immediately equal to 180, and then they converted it. He immediately said, okay, I want my answer in radians, so the measure of a straight angle has got to be pi radians. Because think, if I went ahead and put my circle here, okay, starting here in standard position to get over there, that's just pi, right? That's why he initially set that equal to pi, the x plus 5x. That is perfect. Questions? Is anybody having a hard time? Anybody confused? Okay. Then you have your homework assignment. When are we going to have that due? Friday. Let's try for Friday. Okay. So we'll do Friday, and I believe that's all I got. Oh, come on. There we go. Okay. Let me go ahead and